Welcome to this next video in the playlist on group theory. In this video, what we're going to discuss is the alternating group on the set of 5 elements. In particular, we're going to prove that the alternating group on the set of 5 elements is a simple group. Okay, now firstly let me just say something about the motivation here. So you might be wondering, why is there an entire video dedicated to just proving that this one group is simple? Well, the reason is that the fact that A5 is simple has a huge amount, amazingly, to do with the fact that the general quintic equation is not solvable by radicals. Okay, there is a theory called Galois theory, a portion of abstract algebra called Galois theory, named after Évariste Galois, which is a link between field theory and group theory, and it reduces the problem of deciding whether a general quintic equation can be solved by radicals into problems in group theory. And amazingly, the reason that the general quintic equation isn't solvable by radicals, the reason there'll never be a quintic formula in the way that there is a quadratic formula, a cubic formula, and a quartic formula, translates into the fact that A5 is a simple group. Okay, so that's the reason that A5 being simple warrants an entire video dedicated to it. The next thing to say is that you need to watch certain videos prior to this one in the playlist on group theory in order to be able to understand the proof that A5 is simple. In particular, you need to watch the 4 videos prior to this one. The video entitled Groups of Order PQ, Groups of Order 30, Groups of Order 12, and Groups of Order P squared Q. We're going to use all of what we have learned in those 4 videos to prove that A5 is simple here. Okay, so without watching those videos, there'll be holes in your proof, basically. Okay, so we're going to begin by just studying A5 firstly. Okay, so it's an interesting group in its own right, so we'll firstly get some intuition for what the elements of A5 actually look like, and then we'll actually begin the proof that A5 is a simple group. Okay, so let's firstly start with the study of A5 then, the alternating group on the set of 5 elements. Now, of course, we know that this is going to be a subgroup of the symmetric group on the set of 5 elements. Okay, and it's going to be the subgroup of the symmetric group on the set of 5 elements that contains all of the even permutations. So we know that in an arbitrary symmetric group on the set of n elements, you can ascribe to all of the permutations +1 or -1 a sign, and those that get +1 are called even permutations, and those that get -1 are called odd permutations. And one of the interpretations behind what this sign means is that if you were to split the permutation down into a series of transpositions, decompose it into a series of transpositions, if it's an even permutation, whatever decomposition into transpositions you find, there will always be an even number of transpositions in that decomposition, whereas if it's an odd permutation, whatever decomposition into a series of transpositions you can find, there will always be an odd number of transpositions in that decomposition. Okay, so A5 is going to be all of those permutations in the symmetric group on the set of 5 elements which are even permutations, and therefore when you decompose them into transpositions, into a series of transpositions, they will always have an even number of transpositions in that decomposition. Okay, so how can we actually work out then which permutations are going to be even and which are going to be odd? How can we find the even permutations in the symmetric group on the set of 5 elements? Well, as I showed you in the video on the alternating group previously in this playlist on group theory, a nice easy way of doing it is just taking a permutation in the symmetric group on the set of 5 elements, decomposing it into its cycle decomposition, okay, and then looking at the lengths of the cycles, subtracting 1 from the length of each of the cycles, and adding all of those lengths of the cycles, subtract 1 together. If you get an even number, it turns out that the permutation will be even, and if you get an odd number, it turns out the permutation will be odd. And if you want an explanation as to exactly why that is true, go and watch the video on the alternating groups. Okay, right, so that's how we're going to actually find these permutations that are even permutations. So let's now characterize the elements then of A5. So firstly, let me just say how many elements are there actually going to be in A5, how many elements are we actually trying to find here. Okay, well of course the alternating group on the set of 5 elements is half the size of the symmetric group on the set of 5 elements, because half of the elements in the symmetric group on the set of 5 elements will be even and half will be odd. So the size of this is 5 factorial, which is 120, so the size of the alternating group on the set of 5 elements is going to be 60. Okay, so I need to find you 60 elements, and don't worry, I'm not going to list them all off. I'm going to characterize them, because actually there's only 4 different types of elements here. Okay, so I'm not going to list out all 60, but I am going to list out the 4 different types of elements in the alternating group on the set of 5 elements. Okay, so the first one is the identity element, which I will just denote 1 here. Okay, so that's always an even permutation. You can build it out of 0 transpositions. Okay, and 0 is an even number. Okay, and another explanation as to why it's a even permutation is that if you actually were to construct its sign, of course what you'd construct is the polynomial delta 5, as we explain in the video on the alternating group, and you'd look how many terms are flipped by the identity. Well, of course none are flipped by the identity. Okay, so it'll be a +1 sign. Okay, finally, you can also say it has to be in the alternating group on the set of 5 elements because it's a subgroup. Okay, so you must have this element. Okay, so the identity element is the first element, so we're now down to 59 elements that we have to find. Okay, let's have a look at some more. So, as I say, the way that we can find even permutations is by decomposing elements into their cycle decomposition, taking the lengths of each of the cycles in the cycle decomposition, subtract 1 and adding them all together. So I claim that another great class of elements in the alternating group on the set of 5 elements are going to be what we will call the free cycles. Okay, but really these are going to be elements which, when you take their cycle decomposition, have a free cycle in them and then 2 one cycles, but we don't usually point out 1 cycles, so we'll just call these elements free cycles. Okay, so let me give you some examples. Okay, so let's actually draw some pictures here. So here is the set 1, 2, 3, 4, 5. Okay, now obviously I need the codomain, which is the same set here. And now the set permutation that I'm going to consider is the one that sends 1 to 2, 2 to 3, 3 to 1, so there's our free cycle, and then fixes 4 and 5. So clearly the cycle decomposition contains a free cycle, which is the free cycle 1 goes to 2, 2 goes to 3, 3 goes to 1, and then it contains 2 one cycles where 4 goes to 4 and 5 goes to 5. Of course we won't actually show those. So if we were to ask, is this even or odd, of course this is going to end up being even, because any free cycle can be built out of 2 transpositions. Okay, you could swap 1 and 2 firstly, and then swap 1 and 3 secondly, and that would build this exact element here. Okay, so all of these elements which consist of a free cycle and then 2 one cycles are in fact going to be even permutations, and therefore are going to be in the alternating group on the set of 5 elements. Now, for this one here, you will have a pair, a partner if you like, that will be with it. Okay, and I'll show you its partner. Its partner is itself squared, so let me just draw out its partner here. Okay, so its partner will now have 1 going to 3. Okay, so we've squared this one, so 1 would go to 2 initially, and then 2 would go to 3. 2 would go to 1, and 3 would go to 2, and 4 and 5 would remain fixed. So this is its partner, very much so related to this one, just this one squared, and of course in cycle notation this is 1, 3, 2, just swapping around these portions here. Okay, so here is another element that will be one of these even permutations because its cycle decomposition is a free cycle and then 2 one cycles here. Okay, right, so there are 2 elements of this form, a free cycle with 2 one cycles. What are all the other elements? Because I want to work out how many elements overall are of this form, a free cycle with 2 one cycles, because these are all going to be even permutations and therefore are all going to be in the alternating group on the set of 5 elements. Okay, so I want to characterize all of them. I want to know how many are there actually going to be. Okay, well, to work that out, let's think about what characterizes these. Well, what characterizes them is which two elements you're going to fix here. In this case, we fixed 4 and 5, but we didn't have to fix those two. We could have picked other ones to fix. Okay, so in fact, all we need to work out is how many different ways, how many different pairs are there that you could choose to fix, and then the other 3 elements are all going to be involved in the free cycle, and then there'll be 2 different free cycles, one of them and then itself squared, so there'll be 2 partners if you like. So really all we need to do is work out how many different ways are there of choosing a pair of elements to fix, and then all we need to do is multiply that by 2, because for each of them, for this choice, for instance, where we fixed 4 and 5, we have 2 free cycles. Okay, and then we will have worked out how many free cycles with a 1 cycle and another 1 cycle there are, and those are all going to be even permutations, so they're all going to be in the alternating group on the set of 5 elements. Okay, so the question now just becomes, how many ways are there of choosing a pair of elements from a set of 5 elements? Well, of course, that's just 5 choose 2, but rather than just using formulas, let me explain exactly how to work this out. Okay, so all you have to do then is choose 2 things to fix. Okay, so there are 5 things that you could choose as your first thing to fix. So you'd have 5 different things as your first choice of what to fix. Once you've chosen the first thing to fix, say we've chosen 4 here to fix, we then have 4 remaining things to choose as our second thing to fix. So you would think that it would be 5 times 4. That's the number of ways of coming up with pairs that you can fix. But there's a problem here, there's a subtlety that you need to be aware of, which is that you will actually overcount everything by 2. And this is the reason. In this way of counting, you would count picking 4 first and then picking 5 as your second thing as a separate pair to picking 5 first and then picking 4 as your separate thing. This takes into account the order in which you have chosen the elements that you are going to fix. So it counts 4 as being the first thing that you've picked to fix, and then 5 being the second thing that you've chosen to fix, as separate from picking 5 as being the first thing to fix, and then 4 as being the second thing to fix. And of course we don't want that. Okay, they should not count as 2 separate cases. So we're going to have to divide by 2 here. And of course the answer we will get is then 10. So overall, the number of ways of picking a pair of elements that you're going to fix is 10. Okay? Now, of course, what we're going to now do is multiply back by 2, because we don't just want to know how many ways are there of picking a pair of elements to fix. We want to know how many elements are there of this form, a free cycle with 2 1 cycles. And of course, once you've chosen a pair of elements to fix, each of those has 2 free cycles, because the other 3 elements that aren't being fixed, they can be in 2 possible free cycles, which correspond to this one here and this one here in the case of we picked 4 and 5 to fix. Okay, so now we'll multiply back by 2, and we'll overall end up with the conclusion that there are 20 elements of this form, a free cycle with 2 1 cycles. And if you like, you could go through, if you don't believe me, you could go through and actually work these all out. Okay, as long as you're logical and strategical in how you do it, you will find that there are 20, unless you make a mistake. Okay, right, so there are 20 elements of this form, a free cycle with 2 1 cycles. Okay, and this is what I mean by, I'm not going to list out all the elements of A5, instead I'm just going to categorize them. So this is effectively listing 20 out all in one go. I'm not going to actually list out all 20 of them here. Okay, there's one great big category of elements in the alternating group on the set of 5 elements. Okay, so we've worked out now 21 different elements in A5, so let's find some more elements now. Okay, so the next category of elements, and as I say, there's only 4 categories of elements, so we're halfway through now. The next category is the double transpositions. Okay, those which are made up of 2 transpositions side by side, okay, but distinct, not intertwining. They are acting on different elements of the set, and you'll see what I mean when I've shown you one of these. Okay, now these, as soon as I show you one of these, you'll realise instantly that they have to be even permutations. It's even more obvious than it was for the free cycles and the 1 cycles. Okay, so double transpositions. Let me give you an example, a nice example. So again, we have our set 1, 2, 3, 4, 5, and here is an example of a double transposition. We swap 1 and 2 around, and we swap 3 and 4 around. So this is what I mean by them being distinct. This transposition is acting on 1 and 2, this transposition is acting on 3 and 4, rather than, for instance, this second transposition acting on 2 and 3. That wouldn't be distinct from the first one. And then 5 is fixed. So elements of this form we are going to call double transpositions, where we've got two transpositions in one element, effectively. And it is obvious that these can be built out of a composition of two transpositions. Firstly, just have the transposition which flips 1 and 2 and keeps 3, 4 and 5 the same, and then have the transposition which swaps 3 and 4 but keeps 1, 2 and 5 the same, and that will build you this element. Or of course you could do it the other way around, but that's two transpositions, so it's an even number, and therefore it's going to be an even permutation. So these elements are certainly going to be in the alternating group on the set of 5 elements. Okay, so there's an example of a double transposition. The question now becomes, how many different how many different double transpositions are there? Okay, so again, this is just a problem in combinatorics. Okay, so we have to pick two pairs in this case. So we have to pick one pair as our first transposition, and then from the remaining 3 elements we have to pick another pair. Okay, so firstly, how many ways are there of picking a pair from 5 elements? We've already worked that out. There's 10 different ways of picking your first pair. Okay, so all you have to do is pick a pair of elements to swap around. Okay, so there's 10 different ways of doing that. Then you'll have 3 elements left over. How many different ways are there of picking a pair from 3 different elements? Well, that's just 3 choose 2, which is 3. But again, let me give you the argument, rather than just using formulas, let me give you the argument as to why that is. If you've got 3 elements and you have to choose a pair, there's 3 options for what your first thing that you're going to pick is. There's then 2 options for the second thing to pick, but again you have the problem that if you do it that way, you count the different orders twice as 2 separate elements, so you'll have to divide by 2 and overall you'll end up with 3. More intuitively, look at this. How many different ways are there of picking a pair from 3 elements? You can pick 3 or 4, 4 or 5, or 3 and 5, okay? So just by common sense you can work that out without any maths at all. Okay, so that's the number of ways then it would appear of picking 2 pairs, but there's a problem here again, okay? And the problem is we've overcounted by 2 again, because the problem is that this way of doing it is picking the pair 1, 2 as your first pair, and picking the pair 3, 5 as your second pair, as separate from if you picked 3 and 4, I'm pointing at it and saying the wrong thing. I'll start again. This is counting the option of picking 1 and 2 as your first pair to swap around, and 3 and 4 as your second pair to swap around, as separate from picking 3 and 4 as your first pair to swap around, and 1 and 2 as your second pair to swap around. That's the problem. This is overcounting again. So we have to divide by 2. So of course, 3 times 10 is 30, divide by 2 is 15, so overall that's the number of double transpositions that there are going to exist, 15. And again, if you don't believe me, just do it by brute force, write them all out for yourself, and again, if you do it right, you will find 15 different double transpositions, okay, and all of those are certainly going to be even permutations. So here's category number 3 of permutations that are going to be even permutations and therefore are going to be in A5. Okay, so where are we up to now? We've got 36 elements so far, so we need another 24. I claim the other 24 are going to come from the final category, which is those elements that are 5 cycles. Okay, so I claim we're going to have 24 different 5 cycles in the alternating group on the set of 5 elements. Okay, so firstly let me give you an example of a 5 cycle. So I'll go for the most obvious and intuitive example. So I'll draw out my set 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, and an example would be 1 goes to 2, 2 goes to 3, 3 goes to 4, 4 goes to 5, and then 5 goes back to 1. Okay, and in cycle notation this would be 1 goes to 2, 2 goes to 3, 3 goes to 4, and 4 goes to 5. Okay, just like so. Okay, so there is an example of a 5 cycle. So now the question becomes, how many different 5 cycles are there? So what's the best way of working this out? Well, of course, in this case, I think the best way of actually doing it is to use the cycle notation here. Okay, 5 cycles, you just have these brackets like this, and you put all 5 elements in some position in this 5 cycle. So let's just ask ourselves, how many different ways can we put the 5 elements in the brackets like this? Well, of course, we can put 5 different things in position 1, we can put 4 different things in position 2, we can put 3 different things in position 3, 2 different things in position 2, and 1 different thing in position 1. So that's overall 5 factorial. So we would be able to build 5 factorial, which is of course 120 different combinations of the 5 elements in these brackets, but those are not all distinct 5 cycles. Now, why are they not all distinct 5 cycles? Well, the reason is that this 5 cycle is exactly the same as this 5 cycle, 2, 3, 4, 5, 1, which is exactly the same as this 5 cycle, 3, 4, 5, 1, 2, which is exactly the same as this 5 cycle, 4, 5, 1, 2, 3, which is, just to finish this off now, exactly the same as this 5 cycle, 5, 1, 2, 3, 4. Okay, so I hope you can appreciate why these are the exact same 5 cycle, even though of course they all are different symbols. You've got the elements in a different order, you've got a different permutation of the 5 numbers in the brackets. They all represent the exact same 5 cycle. Okay, they tell all the elements to go onto the exact same thing, and the reason is that we have just sort of rotated all the elements around, so I've just brought 1 to the end, and of course this is really just a loop. It's saying, what this tells us is that 1 goes to 2, 2 goes to 3, 3 goes to 4, 4 goes to 5, and 5 goes to 1. So it's just a loop, okay, that tells us where the elements are going. So it really does not matter if we rotate that loop a little bit, and that's exactly what I've done here. I've rotated the loop round more and more, okay? So all of these are exactly equivalent. So basically there are 5 different symbols that are all the same equivalent 5 cycles. So we're going to have to divide by 5, and of course what do we end up with there? 24. Bingo. Okay, so there are 24 different 5 cycles. You work out these 120 different symbols, you then acknowledge that 5 of them, in each case there are 5 equivalent ones. So for every single 5 cycle in these 120 different symbols, there are 5 different symbols that represent that same 5 cycle. Okay, so you have to divide by 5 to find out the number that you have that are actually different. Okay, and now you've got 24, and that's the number of actually distinct 5 cycles. Okay, and that takes us up now to 60, so that must be all of the elements of A5 now, because we know that all of these elements are even. Oh, and I haven't actually given you the explanation as to why the 5 cycles are going to be even, so allow me just to do that now. Okay, of course we can just now employ our strategy for showing that an element is even. We look at its cycle decomposition, subtract 1 from the length of all the cycles. We've only got 1 cycle here, it's 5. Subtract 1, we get 4. That means that this element could be built out of 4 transpositions. 4 is an even number, therefore this element could be built out of an even number of transpositions, and you can quite easily show for yourself that this can be built out of 4 transpositions, and therefore it must be an even permutation. And the same is true for all the 5 cycles. Okay, right, so those then are the 4 categories of elements in the alternating group on the set of 5 elements. We have the identity element, we have the 3 cycles, we have the double transpositions, and the 5 cycles. So I hope that's given you a bit of intuition for the alternating group on the set of 5 elements. In the next video, what we will do is we'll begin with the proof that the alternating group on the set of 5 elements is a simple group, i.e. that the only normal subgroups that it contains are the trivial subgroup and the improper subgroup.